Good morning, thanks for joining us for the morning session. So this morning we are listening to Dielectric on B2 vehicle for diverrobot collaboration.
Okay. Hello everyone. So thank you for coming. Thank you for the introduction, Ivana. And basically this lecture was, and I was going to talk about the two vehicle for diverrobot collaboration, but the lecture was also supposed to be only 15 minutes at first. So, and now we have a full time slot. So I will also talk about about advancing diverse robot interaction capabilities project that we have at University of Zagreb. We'll just go to the basic concept, provide some motivation, and then we'll review some of the important aspects Adriatic is dealing with it, that with the vehicle design, some wearable sensors that are developed within Adriatic, the sonar processing that is done, and some diver training through virtual reality. I'll also show you some results from last year BTS. So basically, diving is quite tasky. The diver needs to requires technical equipment, right? To dive. He is operating in a 3D environment that is harsh. It has constant disturbances such as currents. Visibility is changing from maybe 15 meters at best down to 0 meters. You can't even see your hand in front of yourself. And in all this, the diver has to do some navigation as well. And usually they will be equipped with a pressure sensor, so knowing their depth, and only a compass. So you can imagine that the reckoning error accumulates very fast in that case. And in the last few decades, basically there were a lot of sensor developments for AVs. So people decided, let's take these sensors and mount it in a handheld unit so that the diver can hold all these sensors and get better navigation. Of course, this way the diver has both hands occupied, and he has to really keep steady these sensors to get optimal performance, which is quite tasking for the diver. So since we have on the other side AVs that are already built such that they have a stable roll and pitch, and they can maintain these sensors quite steady and can provide a lot of very good navigation data, it makes sense to actually just take this handheld unit and just create an AV from it that will just go with the diver. And this is actually our goal, is to create this synergy between a diver and an AV. And way back, even when CADDY started, so in 2014, it was a vision to have like a threefold concept where you would provide some service to the diver in a form of a dive observer, maybe. So basically just all the sensors that you have, maybe even mount some sensors on the diver, collect all this information to create some data sets that you could maybe later on in future use to just model diver behavior, and this way detect some anomalous behaviors and try to maybe help the diver, or at least react in a manner to increase the diver's safety. Also, we want to provide like dive guide. This is quite straightforward because we are doing this to aid navigation of the diver. Basically, he can tell the vehicle, bring me to this point, and the vehicle goes back into this point. And then on this point, probably the diver will do some work. So while the vehicle is already there, why shouldn't it provide also assistance? So we have an option that is called diver slave, or more politically correct now, maybe diver assistant. And in this way, it could assist the diver, maybe just hold the light so that the diver doesn't have to mount it somewhere or hold it in his hand, or maybe even bring the tools from the surface, because During the dive, you are not supposed to go up and down because that's, of course, not that safe. So you can always send the vehicle, okay, bring me this tool that I need for this task if something unexpected happens and you are not prepared for this situation. So when we were looking at implementing these three functionalities, some scientific, applicative, and commercial aspects crystallized. We have a sonar on this vehicle, so we decided, okay, let's do some research in sonar sensing, see how much data we can get from the sonar. Can we actually detect the diver? Can we maybe even segment parts of the diver, get his hands and his feet recognized, and just so that we can maybe reconstruct the pose. We also consider that there are a lot of advancements in the technology for wearable sensors. So we wanted to research new types of wearable sensors that could also aid us to bring new interaction modalities in this pair of the diver and robot so that we can increase their communication as well as their safety. From the applicative side, basically, you can imagine this pair would enhance decision making because the diver can always request the vehicle just make me a small map of the area, come back to me while I do this work. The vehicle makes a map, comes back, then the diver can see the results and maybe plan the next step, what he will do. It can also be a matter of safety. If, for example, you have unexploded ordnance, you are not sure if you can approach it safely. You could always send the vehicle, just maybe take me a small video of this, bring it back to me so that I can investigate and see if it's safe for me to approach. And of course, you can imagine there is a lot of flexibility in combining this. When you have this vehicle on site, you don't have to mount lights, you don't have a lot of preparation. You can always just take the vehicle, position it to just light your work area and such things that will really increase the overall flexibility when doing operative work. And on the commercial side, there are a lot of these wearable sensors that we are researching are very close to commercialization, and they are not available to the divers. So this has big potential to be commercializable. Also, from the vehicle's perspective, maybe you don't want to completely replace the diver body. It's a long way to do that, but you could offer a multifunctional diving tool. At least, do the dive assistance parts, or maybe even just the guidance part, depending on what the divers need most. And since we need communication between the diver and the vehicle, we do this through acoustics, and we use some small acoustic modems that are ready for commercialization. So we also use this project to aid the complete commercialization of that. All of these small modems. So this all started with CADDY in 2014. It was a project coordinated by University of Zagreb, and together with a lot of partners, we investigated the feasibility of using state-of-the-art technology to develop a robotic diving body and to somehow create, a backbone for future diver-robot interactions and research in that area. So we researched, of course, acoustic localization and different methodologies to get the relative position towards the diver. We used the stereo camera for diver detection and also for gesture recognition. So basically, the camera was looking at the diver's hand and recognizing gestures. And also, we mounted a lot of sensors again, some wearable sensors, but not as elegant as the ones here in the Haptics that we do now, to measure physiological data about the diver and also to reconstruct the pose of the diver. So what is the Advancing Diver Interaction Capabilities project? It's funded by Office of Naval Research. And Office of Naval Research is mainly interested in search and rescue and explosive ordnance disposal for their military divers. And this is where this research in CADDY actually comes in handy. So we said, okay, let's extend. Based on CADDY research, we have some lessons learned there. Let's try and correct some of the problems that we had in CADDY and do this through this new project. So what we wanted to extend were basically the vehicle design. We wanted to change it, make it more approachable for the diver. We wanted, as I said, to have movable sensors that will not impede the diver movement as they had in CADDY, that are much easier mounted on the diver. Of course, we wanted to now focus a bit on the sonar. We had a sonar before in CADDY, but we used it as a backup or additional sensor in addition to the stereo camera. Now we wanted to just exclusively focus and see how much data we can get from the sonar. And we wanted also to use current technologies in virtual reality and gaming, maybe to create a training environment, which is much cheaper. You don't want to go, the diver going into water with the vehicle for the first time, and then he will focus more on what the vehicle is doing than on his work that he's supposed to do. So that's for him, and it's also a waste of time. So it's better to get to know the vehicle and also these wearable sensors in a safe environment in an office, just connected to a VR headset. So on the vehicle design front, we developed the second version of this robotic diving body that we call D2. And basically in CADDY, you've got this big vehicle on the left. On the left, it was like 80 kilos, quite large. It was problematic for deployment. You needed maybe 3 people to actually deploy it into water. And of course, it was intimidating for the diver because it's a very big object, and when it goes out of control, as it happens during testing, it's either dangerous for the diver, but also, very scary. So sometimes they had to just duck, so they don't get hit by the vehicle. And so a lot of things happen. 80 kilos is very dangerous. So we looked at, okay, what are the other options? Now with a lot of handheld units available, they pretty much pack the same amount of sensors as body back then had, but in a quarter of the size or even less. So this now becomes one-man portable, at least for a Navy diver, 25 kilos should be one-man portable. And definitely it's less intimidating. You can really take this vehicle if you want, with your hand and protect yourself if something happens during testing. But it's also much easier to use this vehicle in a handheld mode. So you can have one mode where you have automatic tracking and etc. But then you can go back into handheld mode and use the sonar to actually inspect your area, etc. So you get access to all the sensors. And this you couldn't do with the body vehicle before. So our main vision sensor on this vehicle is the Triton Gemini 1200 IK. It's a dual frequency sonar, so you have a lower frequency for pretty much longer ranges up to like 120 meters. This is good to just identify the targets or generally scan the area, and then there we have a high resolution frequency that we can use for cross-lens inspection, or in our case, we want to use this to actually detect the diver and get as much information about the diver pose and relative position to the vehicle. The good thing also is that we have a 120-degree field of view here. In CADDY, we have a 28 degrees field of view, so the diver would easily fall out of the image. And you could, in theory, you could fit maybe 2 divers in the slot of the sonar, but it was hard to achieve. With 120 degrees, now you can probably go track more divers at the same time. So this again goes into the commercialized, as I said, like a multi-purpose tool. So maybe you will not replace completely the diving pair. You have a diving buddy or two divers there, but they could use this vehicle as a tool, and he could track either one of them or both of them during this dive. Component-wise, the vehicle is now equipped with 2 computers. There is a main onboard that does navigation, guidance control, all the sensor acquisition, and similar. And we have added just recently, we're testing here on this BTS, that is JSON NX, that will be dedicated for sonar processing, and maybe later on, when we bring back the camera knowledge from CADDY, also for camera acquisition. We have maybe we have for now one camera on the vehicle, but as you can see, it has 2 eyelids. So basically, a stereo option still exists, or at least a dual mono combined into a stereo kind of option. Propulsion-wise, we have 520 watt-hours of autonomy for the vehicle. and 6,200 thrusters. We usually use these thrusters at like 20-25%. So there is enough autonomy for even more than one dive during operation. Communication-wise, the components that we have on the vehicle are the nanomodems for acoustic communication. We have lights for light-based communication with the diver. There is a screen on the vehicle. I don't know if you can see it here on the back side. This part is actually just a screen, so the diver has access to all the information and what is happening. We can also plan missions on that one and similar. So when using it in handheld mode, this screen is actually the main way the diver gets access to all the information from the vehicle. And also in combination with wearable sensors, we have communications via gestures and haptics available. So first we'll look at the Nanomodem. It's basically an acoustic modem developed by University of Newcastle. It has dual use. You can use it for communication, but also for ranging. So for us, ranging is that it can be used either to get relative position of the vehicle relative to the diver or relative to some anchor that is fixed. In that way, you get absolute positioning. The bandwidth for communication is 460 bits per second, so you can squeeze a lot of info in these transmissions. And when it comes to application, we are doing single range localization to aid the navigation of the vehicle and to localize the diver. And also with two modems mounted, we can play with some time difference of arrival, maybe to get, in addition to range, also the bearing relative to the diver. That way we have also range and bearing from the nanomodem and also range and bearing from the sonar towards the diver. And the good thing is that with this we bound the dead reckoning error, and the more you can bound the dead reckoning error, the more time underwater you can spend. Regarding the lights, we have two lights mounted, and we have two LED indicators. The indicators are used for basic information, like saying that everything is okay, or that we have some system error, or if some command is maybe rejected. One of the lights is used just for the diver, so that we can light the path in front of the diver, and another one is directed at the diver, so we can use it for communication. Divers usually, when they cannot use gestures, they use light communication as some kind of alternative. They usually have preset flashes, like 1 to 5 different flashes that have a certain meaning, or they can use the light actually when they're in dark, farther away, and combine it with some movement. So basically, if we want to do an OK, we could just turn on the light and do a movement with the vehicle, circular movement, and the diver in the distance would see an OK sign, so like a confirmation for a signal. When it comes to other interaction mechanisms, we need to first see what wearable sensors we have, and then what other diver interaction modalities we can explore here. So basically, our wearable sensors are developed by our partner, the University of Auckland in New Zealand, and they use dielectric elastomers, which are pretty smart materials that have a carbon silicon electrodes, and in between, of course, the silicon dielectric. These are quite lightweight and have high elasticity, so you can just mechanically deform them easily and measure the changing capacitance. If you can measure that pretty precisely, as they can, you can get the amount of stretch happening in one of the dimensions that you actually design the sensor. So basically, if the sensor is stretching in another dimension, you will not get a large change in capacitance. And it also works underwater. At least they tested it, and it seems to be a good material for underwater things. So the idea was, okay, let's develop an underwater intelligent glove that could recognize gestures. So as I mentioned on CADDY, we used video for recognizing gestures. In that case, you would need first to put the vehicle in front of the diver, and the diver would need to do a lot of signs. Sometimes he would need to repeat signs. Sometimes he needed to hold this sign, so it's really recognized. So it took some time. This way, when we have local processing, basically the glove is very fast, and it can recognize a lot of gestures It can give some haptic feedback just so you know that the gesture is recognized. You don't have to read on the vehicle screen that the gesture is recognized. So it's very easy to do gesture recognition on this glove. The only downside is, okay, you need to transmit this to the vehicle to actually carry out some command. But since you're doing most processing locally, you actually just have maybe one byte that represents a command that you need to send across, and that's really not such a big problem. Especially when you consider that we use ranging and communication all the time just to get the range relative to the diver. So this acoustic communication is in the background always, so we can just use it to transmit information from the glove. So the first prototype, there are now 3 prototypes for the underwater glove. There is also 2 prototypes for the virtual reality glove, which is a little bit of less material because the diving glove is quite thick, so your hand would get sweaty very soon. So we have a special one for wireless, for virtual reality, and we have one for underwater. They basically contain an inertial measurement unit so that you could differentiate static and dynamic gestures. And a small microcontroller is enough to do the acquisition and processing that is needed. So we decided for gestures to just take a two-step approach. So we have one set of main commands. These are one-to-one relations of gestures that usually divers use. So okay will mean okay, and all these gestures mean the same. The only new gesture that they have to learn is a start communication, which is basically this gesture in a move format, and end transmission, just a static gesture of this. We have to have these guards because when the diver is doing some work, he could accidentally maybe initiate communication. So I'm guessing these having these guards, it's very low risk that the diver will do something like this in water when working with something and activate communication. And even then, if he doesn't end transmission, the cloud will just reject all the commands. In addition to these commands, we have also some flexible gestures that are like programmable in a concept of a matrix. So basically, you could start communication and then say execute the command under 1 and under 2. So there are no new gestures that the diver needs to learn. But also to test how easy it is for the divers to learn new gestures, we also have an option where you could, instead of saying 1, you could actually make some special gestures for this execution. And the good thing about the matrix is that you can basically just fine-tune. If you know what mission you are going to do, and you have like a pool of all functionalities of the vehicle, you can just pick and choose and put them into the matrix, and then just launch whichever action you need. You can always make a small cheat sheet if you forget, and for which row and column you need for some action. The aim, of course, for this is not to learn a lot of new gestures for the divers, because that's time-consuming, and they are already have automatic gesture communication with this set of gestures that they pre-learned during training. So now they will need to do new training and then think about that. And usually when you're diving, you need to focus on what you're working on, not think about which gesture do I want to do now, or what is happening, what is the next step. You need to be very focused, not to endanger yourself. In addition to the stretch sensors, the glove also has a small vibration motor to provide some haptic feedback. This is good for attention grabbing. If we recognize that the diver is, I don't know, following us or something, we can try to grab his attention, ask him if he's okay. So he could then reply whether he's okay. If not, we could react, maybe inform the dive master that the diver is behaving abnormally. And we also can use this vibration for simple acknowledgements, or saying yes or no when the vehicle needs to answer, because keep in mind that the vehicle cannot do gestures. So we need to have this. We have gestures from the diver to the vehicle, but from the vehicle to the diver, we need to find other ways of communication. Then again, we can do pulls, maybe from 1 to 5, and it's also a common way when you have low visibility. You tie yourself with your diving partner. You just have a cord that connects you, And if you want to grab his attention, you just pull on the cord, and then maybe pull once, twice, and after 5 times. So divers also are used to this. And this is kind of a wireless body line. Some products already exist for that, but you can imagine that you could actually use this glove even between 2 divers. You don't need a vehicle, you could actually have communication between 2 divers with this glove. And it doesn't require you to be very close or even to have some vision, like to be straight with a view of both. Apart from this glove, the sensors can also be used for pose reconstruction and for getting physiological measurement. Before it, in CADDY, we had a lot of IMU sensors mounted on the diver. All of these were connected by wire, so it was really a big harness that the diver had to wear in order for us to reconstruct the pose. And then there were a lot of problems. Of course, you need to calibrate this system for this IMUs. You need to use the magnetic part of IMUs, and the diver cylinder air tank is steel and it shifts around, so the magnetic field is changing, and it's very problematic. On the other side, when you have these wearable sensors, you can actually just embed them directly into the suit because they are very thin. So the diver would not see any much difference between the suit and that has the sensors and that doesn't have the sensor. So his movement is now not that much constrained as with the IMU network that we had before. Also, calibration is much easier now because you don't have an independence, you don't have no magnetic sensor. So basically, once you calibrate it, you can either calibrate it on the surface and then go into water and do the dive. As for the price, IMUs can get expensive. These sensors are cheap, but most likely you will need more of these sensors than you have IMUs just to get all the degrees of freedom for pose reconstruction. And actually, our partners, University of Oakland, already developed one prototype that we were supposed to test here, but due to COVID situation, we'll probably move that to next year. And they will do motion, compare this with motion capture, just to get a sense of how accurate the pose reconstruction can be. Okay, so we now have a vehicle, we have all these wearable sensors, but to actually have any functionality, we need to know where the diver is. So we need to do some sonar processing or camera to detect the diver. I will not talk too much about that. Igor will talk a little bit later more about that, but I will just tell you before, we had, of course, as I said, camera. There were problems after 3 meters, 3.5 meters, you could easily lose the diver. And then you would have no information on the diver, you had to rely back on the acoustics again. The benefit, of course, of the camera is that it's more natural. If the vehicle recognizes a gesture, and if you have a special cloth that does that. And there are some benefits if you were always in close quarter, as you're supposed with your diving buddy, then the camera is probably the best option if the visibility will not degrade a lot, because you will always be close to your diving buddy. However, if you remove the camera and maybe take the sonar, you now have a much higher range of operation. You are not constrained by visibility. And in essence, maybe it's a simpler detection because you have a 2D image in comparison to the stereo point cloud that you need to process. You do get only 2D information from the camera. You could get 3D information. But basically, since you have acoustic communication, you transmit the depth, the missing dimension, already from the diver, directly measured. So you can easily reconstruct a 3D position of the diver, even using just the sonar and this information about the diver's depth. So the approach in Adriatic was, okay, let's try and do machine learning and deep networks to maybe just train image recognition to get position of the diver. And for that, of course, you need a lot of data. So we decided, okay, let's build some training database. We had a lot of recordings of the Arizona from CADDY. We recorded new data sets from Gemini. But of course, that's a lot of testing because you need to do manual annotation where the diver actually is in the image, label the diver or other objects in the image. This takes a lot of time, so we are considering now to also research how to use virtual reality to create synthetic sonar images. So basically, this way you have auto labeling because you know which pixel corresponds to what. And it doesn't really have to be one-on-one, 100% replica of the sonar. It needs to be close enough so that you can do a pre-training on a lot of data, and then use the smaller database of maybe 2,000 to 5,000 images to additionally train on real data from the sonar and adjust or fine-tune your network. And it might sound maybe far-fetched, I don't know, but with current results that Igor did, basically he used existing CNN architectures that are pre-trained on camera photographs. And then he just gave it 2,000 samples from the database, the sonar, to just train and recognize the driver. So imagine you have a camera and a sonar, you saw that this with the camera, but still the network managed to get around 80% of precision in detecting the diver, which is a good number considering a small data set for training the sonar, and the fact that actually this network was pre-trained for camera recognition, for just processing cameras. Okay, I will not go into too much detail. I will leave that to Igor. But I'll also cover now for you the basics about the virtual reality that we want. So the good thing is that you can actually include hardware in the loop with that, and you can include the human in the loop as well. So basically, we can use all the vehicle hardware or the vehicle algorithms that we have. We'll just get simulated sensor information from the virtual reality. We can use the same glove directly, and maybe also acoustic, so we get the real delays and all these lower rates that come with acoustic. And the benefit is that you have cheaper training, as I mentioned earlier. You don't need to go underwater, you can do it in office and just get the diver used to the glove and to the vehicle. This is good also for synthetic collection of data that I mentioned just now. And then for continuous testing. And you also get a benefit that you can involve the diver in the system design. So you can just bring the diver into the office, tell, okay, I have here 3 ways that we could interact. Let's try and tell me which one is the best. So you can focus your research quite easily. You don't need to actually have a field trial and then tell you that the diver tells you, oh, nothing of this interaction is natural to me. Why don't you do something else? Okay, and what we implemented this simulator in Unity, so it's a framework that allows quite easy development and somewhat realistic environment. We use the HTC Vive headset and put the diver, and actually this VR was first used for collecting data for training the glove. So basically, our partners University of Auckland took the, as you can see here in this video, took the initial version of this VR concept and applied it to 100 or so people in an open day event where they collected their behavior. So the problem with training the glove is, of course, you can take only one guide and have the behavior, train it, but each of us does a little bit different, all of these gestures. So the glove will be quite specialized, maybe not working on another guy. So if you have 100 people or so, then you can have more general detection of gestures from the glove. And of course, you can always call someone, into the office, and he does just these gestures. It's much easier to, get people involved if you give them headset and then they have some fun around with that. And in background, you get actually the data for that. So it's a common way how they do it in technology. Now with Facebook and everybody is giving you something to have fun and collecting data in the background. So we just have the same concept. Okay, so this is what we are doing nowadays on Adriatic. And I'll just show you some demonstration examples from last year testing. So it was done here at BTS in the pool not far from here. Basically, the idea was to test first if the underwater glove really works. So you can see here an example of the first prototype. Basically, it's a big bulge on the glove. Now with the third version, it's much more slimmer, so it's less intrusive on the diver. Here you can see the diver doing the initial test and just checking if he gets all the gestures. Upstairs on the top side, we are getting through acoustic the commands and just checking that everything is okay. After we have all this done, then we put inside the vehicle. Also the first test for the vehicle in water was this. And basically we said, okay, let's have some gestures random and we'll assign to them some movement. So the vehicle should move back, left, right, up, down. And we also had an option to send the vehicle to like a virtual home, which would be somewhere far off from the diver, and then you could call it back, come back to the diver. So this was the initial testing that we did, and this is photography. During this testing, we also discovered that there is some room for fun. And basically, these two T200 thrusters are way too strong for this small unit. So you can easily use it as a diving scooter. So here you can see we're replicating the subnautical again in real life. And basically, you can go with 1.5 knots with Igor, who is like 2 meters and all his diving equipment with this vehicle if you use 100% of the thrusters. So I'm just putting this so that you get a sense of how much autonomy you actually can have when you're using only 20-25% of the thrust. Okay, so this is basically some demonstration. These are not, I didn't put any plots or something. So just to see that actually some of these things that we mentioned are already in application. And regarding future work, we will of course continue the data collection, maybe be able to provide this training database for other people, because when we started off, there are usually for camera you have a lot of databases for training, but for sonars there are none. So we would like to, when we have it annotated or at least partially, share it, and then maybe someone will also annotate additional raw data for us. And regarding the diving suit, as I mentioned, it will also measure respiration and heart rate in addition to post-reconstruction. We'll probably see that on BTS next year. This year, we'll try to do real-time diver tracking and monitoring. And longer down the road, we're looking at augmented diving masks. So basically, just to add one more modality how the diver can get information, because we can send it maybe to a diving clock, to underwater, like a smartwatch, some information, but the diver still has to look at it. He still has to keep in mind if something is vibrating, to actually pay attention to what is happening. This way, he can get all the information directly, like a heads-up display type, even maybe the intention of the vehicle. So when he does a command, the vehicle, at least you can have like a small pointer on the vehicle to just show what it will do next, in which direction it will go, so the diver doesn't get surprised, if the vehicle does something unexpected. So that's all from me. So thank you for your attention.
Thank you. Very interesting talk. So, are there questions?
This lab that you showed with the mobile device, it's actually product or it's prototype? There was a plot.
The glove?
Yeah, the glove.
Well, there is a company, StressSense, that is producing these sensors, but I think that this lab was just like a demo for the capabilities
Of sensors.
Of sensors, yes. But I can inquire if you can actually purchase gloves from them.
Yeah, thank you.
Okay.
The stress sensors, they give you only a single number change. It's not like 3D or 2D.
No. So if you, for example, we have in a glove now For each finger, you have one sensor, but you can then just detect this. You cannot detect these stretches, right? So you would need probably additional sensors. And it depends. You can go like brute force, then you have 3 sensors per finger, and you're probably safe to get everything, or you can maybe optimize and just see on which fingers you really need to put the sensors, and maybe then get, of course, the cheaper glove. Although the glove itself can go like maybe 1,000 euros in production, or 2,000 euros for these 5, with these 5 sensors, or 6, depending if you want some extra here on the palm. So it's not, I don't think it's that expensive, because you have commercial gloves that are way more expensive.
Is there any way of finding outliers in the communication? I mean, if diver communicates with other divers, or just tries to do something with his hands, can that be mistaken for a command to the robot to come? Is there any kind of chance? How do you read it?
I mean, there is, but that's why we had this, the guards that I mentioned. So basically, if you want to do even an OK command, you need to do like this, OK, and then M communication. And once you do these 3 gestures, then it's a process. So it's a kind of safeguard. Of course, I don't know whether divers can do anything underwater, so it can always happen, you know, that some weird position triggers sensor. But I hopefully, you know, since you have a state machine inside that's actually looking at the syntax of these gestures, and it's not always only, it's not one gesture. Maybe, you know, some panic gesture like stuff could be directly translated, and then, okay, you risk getting false positives, but it's better to err on the side of caution, as I say. Okay.
Anybody else? Any questions? The processing is done well. You still do it outboard, not on the glove.
No, it's done on the glove.
Okay, so what are you using for processing?
Well, I have to ask our partners, but they have a, it's not like a deep network or something, it's some different kind. I don't remember now. But it's just, it is some machine learning algorithm, but it's not something so complex, because it has to run on the microcontroller. It's there. So basically, it's some kind of branching, I think. So when you do that, and when it gets some measurements from the fingers, then it branches off until it gets a final result that is one-on-one, so that it doesn't have any ambiguity.
Okay, thank you. Anybody else? Let's thank the speaker again. Okay, so next speaker is Orsag. He received his PhD from University of Zagreb, Faculty of Electrical Engineering and Computing, where he is currently working as an associate professor. As a researcher, he has been involved in various projects financed by the National and International Science Foundations and industry. In 2011 and 2012, he worked as a visiting researcher at Drexel as a recipient of the Fulbright Exchange Grant. He was a PI for EU Horizon 2020 Cascade funded project in Gorse, and is currently the PI of Project CADDY on the Great Preparation Science Foundation. He is involved in several EU projects, Aero20, Core, AeroCore, and Robocom. He co-authored over 30 scientific and professional papers, including journal and conference papers on mammography in robotics, and a book chapter in the field of unmanned aerial systems in robotics. He was the recipient of Croatian Academy of Engineering Young Scientist Award Vera and Hamidas, and he served as a committee of several international conferences, and is serving as an associate editor of Maritime. He is a member of IEEE Robotics Area Topics Group, and is serving as the chair Corporation Section IEEE, RAS, and as a national coordinator of European Robotics.
Thank you. Okay, first, I have to put a disclaimer. This presentation contains video that might be sensitive to people that participated in yesterday's party. So it's going to be a bit tricky. Oh, okay. Better now? Okay. So basically, what I would like to talk about today is a structured greenhouse, a new type of paradigm for indoor farming that uses a lot of different robots to achieve a certain task for farmers. So basically, the idea for this was, okay, when you look at the future of agriculture with all the climate change and everything, there's quite a lot of companies now that try to invest in fully indoor farming. This really means you don't use light, you use only chemicals and other nutrients that you can, chemical nutrients you can put in the plants. You're not really relying on anything, let's say, natural. You're trying to completely industrialize farming. And this has been done in couple of companies. Maybe New York is one. There's one salad company in New York. They can really produce salads without any introduction to the sun or any outside conditions. Not only that, they can really track each and every salad, basically what they put in it, when was it grown. Like all the information is provided to the customers, and to have something like that is probably what we're going to face in the next couple of years. And really, this is because farming is labor intensive. So you want to decrease the intensity on the farmers. And if you want to do all of this in a more, let's say, natural or eco-friendly way, you need to put a lot of labor there. And this is not popular. We're a generation of people that like to work on the phone and in the office, and we really don't want to go in the field and dirty our hands. So basically, farming is not so popular in these days. The idea for the project, when I was looking into what I can use heterogeneous robotic systems in, then farming came up, and then I ran across this information that hasn't really has been fact-checked by historians, but there's a lot of it online you can find about Empress Tiberius and his love for, well, let's say cucumbers. And basically, what he wanted to have was cucumbers all around year. And this wasn't possible at the time. So but he forced his slaves to make it possible. And the way they did it is basically when it was cold, they would use some kind of proto-glass material, and then they would take the plants and put them below, underneath that, and the sun would keep them warm. But when the warm weather came out, they would have to move that, put them outside, get some air in there. So basically, they were working every day, putting cucumbers back inside, making them warmer, and cooling them when it was too hot. And in theory, they achieved something like that. They literally expanded the year that they could grow them. So, of course, this was done through slavery. And Jula mentioned this earlier, so it kind of tracked my way into this. I've come across that in IT today has really been a lot of effort in avoiding the use of a master-slave type of nomenclature. And I think this is quite ironic in the robotics world because the whole term robot basically comes from slave. So when we try to push this in the robotics community, we have to teach our US colleagues that really only because the word robot doesn't mean slave in English. It doesn't really mean that it's also not probably offensive to some people. So we really need to make some things clear to ourselves before traversing in this area. So basically the idea of heterogeneous robotics. And the idea is not here when we're looking into other ways where we can use this is can we achieve something like that in farming? So in Spectralaria, what we want to do is we want to have ground robots, aerial robots, and robotic manipulators working together in order to take care about our plants. And since we are indoor, we can fully structurize the whole farming process. And we can optimize the farm. This is something that people have been doing ever since we started farming. You might know from your high school or middle school that certain revolutions in agriculture were when we learned that actually we can have part of our land not growing anything for a while, then this part of land would kind of get more nutrients for the second stage. And we actually learned that crop rotation, rotating where we grow what, actually produces better yields. And when we learn more about the plants, then we realized, well, we don't really need to do crop rotation in the sense that part of the land is remain barren. No, we can actually choose which plants we plant where, and each plant uses different types of nutrients from the soil, so we can keep the soil healthy by not rotating crops, but just putting different types of crops in different places. So that this produces obviously more yield. And in the greenhouse, we don't actually care about the ground. We bring the ground inside. It can be always healthy. But since the plants are inside, we need to, each plant requires different types of outside conditions, different types of sun, water or moisture in the air, windy conditions, quality of the air. Those are quite parameters that we can play with. And we can devise algorithms that can give so the farmer says, I want to grow tomatoes, peppers, blueberries, eggplants, and I want to grow this much of it. Can you please find an optimal organization of the greenhouse so that I can place them, so I can put all this there, and that every plant gets the best from the outside environment, from the sun, from the moist, and from the wind. And taking that into account, we also want to organize this greenhouse so that the robots can actually get each and every plant, so they can get to the plant, move it around, and play with it, basically. And of course, the problem is it's not as simple as this, but you can really observe how it can explode quite easily by just, if you have the amount of cultures that you want to grow and you try to expand your greenhouse, the amount of combinations that you get increases exponentially. So it's really intensive to try to optimize this way. And then for each and every farm map, matrix M here, which actually says, okay, we have 3 cultures, 1, 2, and 3, peppers, tomatoes, and eggplants. And I want to find a structure where I have 3 by 3 squares of organization in the greenhouse. where will I put each plant to get, this is one combination. Then I put it on a cost function and try to see if my plants get enough nutrients in this setup. And I try to find every combination that works. So it's a fairly simple robotics problem that can be applied to farmers. And what we need here is a ground robot that actually goes around these cells, picks up a plant, and brings them to the manipulator that treats it. So we've adapted standard Pioneer robot for our purpose and for our use case to be able to pick up plants and move them around. And of course, this is one example of a setup, a fairly simple one for our rather small greenhouse that we have in Bologna. The points that you see on the left are what we call points of interest. So the robot can pick up a plant if it reaches the box from any of the points of interest. And since this is this setup is working for a couple of months until we grow everything, so it's fairly structurized, and we can use we can plan it ahead and have all the trajectories known in advance. And then we can tell the robot when he needs to pick up a certain plant to follow one of these trajectories. And this, in theory, this is how it looks like. So we tested this through simulation. We applied a simple 2D photographer on it to localize the robot. It goes underneath a box that contains plants and shifts it around the greenhouse. Yeah, the instructions come from a farmer. So the farmer says, okay, this plant is not receiving enough light. Can you move it over here? And then the robot goes and moves it there. It can also be fully optimized, where the farmer says, I want this amount of yield from all of these cultures, and I can train the network to learn how to grow it in the optimal way, and then the robots work themselves around. This is the mechanism that we designed for the Pioneer robots. We work with Pioneer robots because we have them. And our setup is easier in that way. It really drives underneath the holders that we keep the plants, picks them up, and traverses them and brings them to other points of interest. This is how it looks like in the current, let's say, a humble version. Yeah. This is actually, we use this science like this. This video. So it's quite easy to make it work. Now, once we are able to move plants around, we want to be able to do something with that. And this is the soft robotics component of the project. So we want to be able to take the plant with the robot, pinch it. Okay, the easiest things you can do is you can pick the fruits from the plant, but there's other type of agri-technical measures that you can do with robots, and you need soft robotics for that. Marcela gave a really nice presentation about the soft robotics component, so I will skip this. I'll just try to briefly mention some certain points that are key for this project. So we're trying to develop, let's say, type of skin on the robot hand that allows us to mimic the human sense of touch. And really in nature, I think human sense of touch is probably the most developed sensor that we have compared to other animals in nature. We are very good at reading the data from our fingers. And it's amazing how much information you can get from that. So what we're trying to do is we try to teach our robots to work with soft sensors and repeat certain actions farmers do on the plant. So for instance, cleaning or removing excess fruits, pincing flowers, which is also sometimes important. So there are different types of agri-technical measures that you can do. And it's obviously not novel. People have been trying to automate this process since the last couple of decades. However, the way we approach this problem is we want to have a robot with different tools for different types of fruit, different types of agri-technical measures. It's really hard to repeat certain things on different cultures. And then this is really hard when you try to generalize the problem. So we need to have better sensors and better sense of touch and better actions with what we have so far. And of course, augmenting the manipulators is one aspect. The other aspect is trying to understand the plant. So in order to be able to understand the plant, we need to build huge data sets and train the networks to learn, okay, this is a stem, this is a fruit, this is a flower. The robot can approach from this angle or from this angle. It can pick this thing, it can pinch this flower. So in order to be able to do this, we would need huge amounts of data, and that needs to be annotated. And this is really cumbersome, it's expensive, and it takes a lot of time. So the approach we're trying to take is, why don't we try to model things and then try to generate data sets artificially from these models, and that can be used to be annotated almost instantly when we produce images and everything that's training the network. So what we do is we model, for instance, peppers. We model stems of the plant. We model the leaves of the plant. And then we use 3D modeling software to kind of produce pepper plant automatically for us and generate randomly where they put leaves, where they put peppers, of course, following certain rules, and each plant has certain rules how it grows. Now, the process is not ideal. As you can see, there is some flowers on the bottom of the model, which it doesn't make sense because farmers would remove that almost instantly. And it can kind of produce what we call a functional model of a plant. And it turns out that even this relatively poor models of the plant can actually be good to train them, to train the networks, artificial intelligence algorithms to learn the parts of the plant. We also work a lot with photogrammetry to try to model so in modeling, you can do it by hand, or we can model what we have. So we pick certain fruits, and then we can try to produce 3D models, and then we go back and produce a complete model of the plant and try to feed it to the algorithm. So the key point here is to avoid annotation. Annotation is done automatically when the models are built. And what we want to be able is, when the robot picks up the plants, it can bring them to the manipulator. The manipulator can learn where everything is, and it can apply certain operation on the plants. Of course, we rely. So this can be done. Maybe each plant can be viewed once in a week or once in 2 weeks. But in farming, it's really key to immediately detect pests or detect problems with the plant. So it's really important for the farmer to know the state of each plant in every time that he wants. So for that, we use aerial robots. And since I come from aerial robotics and aerial manipulation, so the approach that we were taking is putting arms on the robot. This allows us to perform certain actions on the surrounding world. This is a lot of times what we really want to do in this project with it is we want to have a manipulator that goes outside, goes away from the propellers, so it's capable of reaching the plants without ever flying over them, because flying over them protrudes them, maybe maybe pollinates them when we don't want, or just harms the plant. So we want to be able to fly below and then take images of the plants. And for that, we devised certain algorithms that allow us to plan separately the motion of the body and the motion of the end effector. And in this experiment, we repeated a classical peg and hole problem, which mimics the way you want to approach a certain plant. The end effector, we're trying to keep it so that it can go in the hole without ever harming, by also including the dynamics of the vehicle. So when you plan everything, you plan like a quadrotor is moving in hovering motion. But in reality, it doesn't really happen that way. When the quadrotor moves, it needs to pitch or roll. So once we plan simple trajectories, then we apply simulation, or we run the simulation on them and see how it will actually play out. And then we use the null space of the manipulator to counteract the motions of the UAV, and then the manipulator moves the way we want it to move originally. And this will, in theory, allow us to film the plants in real time, each plant when we want it and how we want it. And so, of course, this is an example of one project that they're using drones to plant stuff. Our idea originally came after working on Structurized, came on if we want to put out a fire with precision bombs that actually put out fire. So we want to be able to say I want to throw that ball on that exact position where I want it to land. Another project that just started, August Park, we are applying similar algorithms for detecting and forming a structured model of the plant. We're applying these algorithms on wheat, which is very important in Croatia. It's an important culture in Croatia. The problem is there's not a lot of modeling done on the plant itself. So the farmers, they want to know what type of nutrients work best for it. And what we're doing is we're growing a lot of wheat We're forcing a lot of pests on it, and we're degrading it with nutrients and trying to see what happens to it. So the plants are harmed in this project, and we're trying to learn from this how to actually grow good wheat. It's actually an interesting project, but trying to build a structured model of this plant is much harder than, for instance, pepper that has really nice looking fruits and everything. This is very hard. And maybe the future of application is Project Hector and one other project, Orchard Scout, where we're trying to push this paradigm from the greenhouses to outside world. So we want to have mobile robots equipped with manipulators and doing regular inspection and maintenance on the plants. This is much harder than in the greenhouse because there's a lot of unstructured problems here, but some techniques can be applied to achieve similar results. So we also want to be able to build functional models of the plant by just taking a lot of images and forming 3D models from it. Inspecting them. So inspection is really a very big problem in farming because it requires a lot of labor and it needs to be done all the time. And that's it. I'd like to thank these three people that have done the most of the work here in the entire lab. And I'll take your questions.
Thank you much for the interesting questions. Okay, so we have a question for Structurized. So for the project officer, will you serve the food from the orchard, or how will be the final level?
Yeah, that might be interesting.
So the precise object dropping that you mentioned for putting out fires, right? I can't help myself but think that people in recent past have mastered this skill of precisely dropping objects from air to specific locations. Did you try looking into some of these existing algorithms that have been used for morally questionable purposes, or
yeah, of course, yeah. A lot of however, a lot of this, when we looked into this area of research, a lot of it really focuses more on missiles and guided missiles. Here we have basically bomb dropping, which hasn't been so much scientifically researched, let's say. There's probably a lot of military usage for it. It really resembles that. It's basically that. But surprisingly, there's a lot more information about where you land parachutes and other things like that. Not really when you have something bulky moving around. And you don't really have in UAVs. You can really control a lot of motion on it. So you can when you fly and then you stop. The motion, the stopping is pitching, it produces angular motion, and you can use that angular motion to increase the speed on the it's called bomb, and that gives you some interesting directions that you wouldn't be able to achieve with, I don't know, a plane or a helicopter flying horizontally. This is unmanned, so you can really do crazy flying stuff, and then you can use this motion to direct the parabola of the bomb. Let's call it. But the idea really isn't bombing stuff. Well,
Marco, I have one curiosity. In your opinion, what is the hardest fruit to cultivate indoor and to use with robotics? I saw some examples yesterday of grapes, tomatoes, peppers. So, is there like maybe a high grade where it's hard, but it will be very good to do that fruit because it's very costly fruit?
yeah, I can't really speak from for the entire world perspective. I can still we work closely with one creation company, CADDY, that that covers, let's say, Central to Eastern Europe. And there, let's say, the biggest challenge that they always give us is the blueberries. They are very lucrative. You can earn a lot of money from just a single plant, and they're very labor intensive, especially for picking. But different plants require different type of agri-technical measures. For instance, peppers, from personal experience, are great because they are very resilient. Even beginner farmers like us can grow them easily. But when you try to pick them, and you saw from yesterday Marcela's presentation, it's really hard just to pick a single pepper without harming the rest. So the peppers, they usually grow together, and there's more fruit coming where you pick the pepper. And they're very hard connected to the stem, just like eggplants, for instance. Eggplants, you can't pick from your hand, you have to scissor them. Peppers you can pick, but you need to apply it in a certain motion that breaks the stem connection. If you use any other motion or any other direction, it will destroy the plant. So that's why people actually cut them automatically. But if you had a manipulator that can find where a stem is, how it's directed, then you can really find an optimal way of just picking it. Different problems, different, yeah.
In the greenhouse indoor scenario, what capabilities does using drones bring, as opposed to just having a mobile manipulator going around?
Yeah. Recently, one, I think, Australian company sold a patent on micro UAVs around the greenhouse. They fly around and kill flies. So they find flies and they run into them. And this is multi-million-dollar business, because just a single fruit fly can destroy 20 or 50% of your greenhouse, just a single one. So it's, if you saw in the video, we have this stickers to collect flies. It doesn't work that good, but if you have something moving around, finding flies, running into them, killing them instantly, then you're good. So that's probably the biggest advantage you can have from UAVs in the greenhouse.
So you clear them, I would like to thank the speaker again.
No. Nisam isključio, da sam vidio što da. Prezentaciju. Da, super. Može, a kako imam?
Okay, and the next speaker is Slošić. He's a PhD student at Robotics at the University of Zagreb. During his bachelor and master studies, his background was mostly automation robotics. In the second year, he participated in the Erasmus student exchange at Karlsruhe Institute of Technology. And this went to robotics, he tried his hand at optics and photonics during this exchange. After graduating, he is taking part in one of the startups where he gets involved in marine robotics. He started working in a spin-off, H2O Robotics, and shortly after, he decided to enroll in the doctoral studies in Robotics. Today, he will be doing a PhD presentation, production testing, and possible use cases of underwater.
Thank you. Okay, so production testing and possible use cases of underwater acoustic beacons. Here's first the presentation content. First, a few things will be said about motivation, underwater acoustic beacons themselves. We like to call them pingers. Testing locations and the results, pinger-based products, and some possible use cases of pingers. So, the motivation was at first the improvement of underwater localization and communication, because all the existing modems that could be found on the market are usually really expensive, and that's certainly another thing that we want. Second thing was divers' need for safety and easier communication with other divers in the outer world. And the third thing was idea to make a device that is simple to use and easy to integrate in already existing systems. On the picture we can see the pinger. It's an acoustic nanomodem in combination with electronics that provide Bluetooth connection with other devices. It can range up to a few hundred meters, and it's used for underwater communication and diver logging. It's wirelessly charged and connected, and it's used for the production of the products at the moment at H2O or H2O Observe and Orology. On the picture we can see the testing on the Lake Chiche, and that was the usual setup we used in last two tests. And of course, we did some testing in the laboratory, but that was mostly testing of software and mechanical and thermal tests. On the picture, we can see apex. Usually, the setup was that we had two fingers, one that was downside, that was simulating the diver, and the other one that was, or the other apid was the topside finger that we could connect to, and we log the data on the apid from that topside finger. This is the picture of our test in Chiche. On the left side, we can see the buoy that has a finger hanging on itself. It's somewhere here. And on the right side, we can see the equipment that we used. Here are some of the testing results from PAC that was conducted 2 weeks ago. So there are a lot of things on this plot, but we will start with the blue line. The blue line is the apid that was moving freely. So there's a topside finger, and we were driving the apid, and he was ranging the anchor finger that was downside, and there's this red spot. The yellow spots show the places where we got a ping, so where we got a successful ranging from the anchor finger, and the green lines just represent how the range was big. So we see that all the ranges cross in exactly the place where our downside finger was placed. What actually makes sense because that was the location of it.
This is the same picture, just without the green circles. I put it here because I just wanted to show how some ambiental noise and configuration of underwater terrain can affect the measurement itself. This test was conducted in pretty much shallow water, so the depth was around 10 meters. And we managed to get a range around 600 meters. That would be this part that was still constant. And we see those parts that are blue, so we didn't get any range messages here due to some boats passing by or underwater barriers or something like that. On this test, we got pretty good precision. So the biggest error was around 1 meter with variance of a little bit under 10 centimeters. This is the group test. In this test, we used one APED as a top side, and we put 3 anchors under the water. So each color represents the location where we got the thing from. We got the successful ranging from any of those 3 fingers that were anchored on the buoys. So we see at the beginning we are getting all the signals, but as the time passes by, only some of the fingers are left. So it depends on many factors. First is battery status. The second one is, of course, the direction of the fingers, how it floats in the water. So just if we zoom this part of the picture, and if we add those circles from the previous slides, if we see the range here, so okay, it crosses here, so we can see one finger was here, the second finger was here, and the third one was placed underwater here on some depth. The last test we conducted on PAG was the depth test. We took 2 fingers, one H2 observer and a Rologia, on the depth of 105 meters, and they were placed there for a couple of minutes just to see how this pressure will affect them. We got all the results, so in that moment there wasn't any problems, but later we found out that there were some air pockets inside, but I'll mention that later. So regarding the testing in the laboratory, after opening up the fingers that were problematic, we saw that some air pockets are left inside, even though we used the vacuum chamber. So at the moment, we are also testing the thermal expansion during the charging, because we also assume that it will also cause some problems that we had. At the moment, we are redesigning the prototype, so there's the temporal status of it. At the Lake Chichen Island PAG, we noticed, as I already said, that ambient noise can affect the measurements and underwater terrain too. Also, the penetration of water is fascinating. Really, water finds its way. And the quality of potting compound is really important regarding the temperature, and in general, all atmospheric factors are taken in account when potting is going on. So now I will say something about finger-based products. First one is H2 Observer, is the one that we saw in the first picture. It's an acoustic modem, and it was main use was for logging divers data, and it comes with a dock that's this thing here, and it connects to a mobile app that provides the data to somebody on the boat or on the surface to see where the diver is. The second one is Rologia. It's pretty much the same electronics, just a little bit reconstructed to fit the needs of the diver side. So it has this red part that is meant to fit the Garmin watch,
and it connects to it over the Bluetooth. And so it looks like this. We get a ranging message on the screen, and this is the octopus who wants to eat our finger. But yeah, it didn't taste so good. And this is H2 orbit. That's the last product that we are trying to produce. It's the diversion system buoy that is meant to be the connection of the diver with the real world. And all the time when the diver is underwater, the orbit follows it and locates it using the two fingers that are placed under the shell. So this one on the back. Possible use cases are underwater Internet of Things, and that would be the most probably the topic of my research as I enrolled in the PhD studies. So what of those topics we saw yesterday and today, and in general, every problem itself is special. So we hope that H2O Observe and Ecological will fit that, because at the beginning, as I said, it was idea to make something that is easy to integrate in already, in already existing systems and with not that much cost. Thank you for your attention.
Thank you. Questions? Okay, I have a question regarding the finger. So, how long the battery lasts?
Excuse me?
The battery on your finger for radiation?
It's highly correlated with it's highly correlated with the number of things it does. So if you're in continuous mode, so if the diver is underwater and it's constantly sends a signal for raging, it will last. We use the fingers for 2 days without a problem. One was on low battery at the end, but some of them are still working, so it's pretty much low energy. It's efficient. Yeah, so
But you could extend the battery significantly if you do it like continuously.
yeah. But as we were on testing, we really pushed it to the limit, and it was working fine.
So when it comes to the mechanical construction of fingers, can you tell us what are the main challenges when building one?
Yeah. So the first problem is the potting compound that really has to reach every part of the finger. We had problems with some fingers, and when we opened them, even though there was a free space and vacuum chamber used, we saw that compound itself didn't find a way to all the places. So at the moment we are doing the redesign regarding that problem. And the second thing was the heating. So as finger is charged wirelessly, a lot of heat is dissipated during the process, and the potting compound itself, when it hardens, it doesn't have as good thermal properties, so it expands a lot and it shrinks. And we really saw on the fingers that they kind of deformate when they charge. So yeah, we are looking. We want to change the design in order to escape from those problems, because as the things are now, it looks like the potting compound comes around the components, and as the temperature goes high, it literally rips the components off. Those are not like big changes, like regarding the position of the component on the chip, but still we notice when the finger gets hot, then things are not working. When it gets cold, then everything is working. So obviously this mess itself is really oscillating. So we are trying now to isolate those chips and all the electronics inside to save it from those mechanical. Most probably caused by thermal expansion. But still, we don't know what's happening because when we pot it, it's really hard to investigate what is inside. So yeah, it's not the fastest process, but yeah, we learned a lot during the examination of the broken ones.
Somebody else?
Okay, so my question is regarding the charging. Since you chose the wireless charging and since it's rated such problems with the heating, do you consider maybe switching to other modes of charging, such as wire charging with the screw that you showed before?
Yeah, so the wired version is coming. I didn't put a picture because it's not finished yet. But in general, underwater connectors are really expensive, unbelievably expensive, and they would add a lot of price for like not as big change as we predicted. But yeah, if we don't manage to solve the problem with the overheating, we will then definitely move to wired version.
Let's thank the speaker again. This concludes our morning session, and we are invited to go for coffee. See you later. The next one starts at 11, so please be back there. Thank you. Что-то в гости, что ли?